on the world of spin and memory devices. And spin and memory, two different words here. So the spin here that I am referring to is the spin uh, predominant of an electron in this case. And why I am referring to this spin is because I will be and as I was introduced that my research interest lies on this spintronic devices, which is basically a form of electronic device where we harness the spin of an electron instead of the charge of the electron, and therefore these are called spintronics, or in a hyphenated manner it's spin electronics. Okay, so there we harness both the intrinsic spin of the electron as well as the orbital spin, and sometimes both of them can be coupled together, and we have something called spin orbit coupling. But we will not go into the very details of all of this. However, we'll try to see what are the effects it brings and how this can be used in different devices, and how they're being harnessed. Already there are some products in the market. So yeah, so the next thing is I will skip these slides. Yeah. So the first thing is to understand what is the difference between a spin transport and a charge transport. We are all familiar with charge transport. We use the charge of an electron, and the absence of it, let's say, is called holes, or in some cases we can use the ions as well as positive charges, but we understand this very well, what the concept of charge based transport and charge based electronics. But in a spin based transport or spin based electronics, we harness, as I said, only the spin of the electron, and we all know that electrons can have the up or the down spin. That is the nature of its, I mean, that is how the nature of it is. It comes directly from the quantum nature of it. And that up and down electrons is sometimes referred as the north polarity, south polarity, sometimes referred as the up spin or the down spin. There are different nomenclatures for it throughout the presentation. In other presentations as well, you might see these different nomenclatures. So up spin, down spin, north spin, south spin, these are all nomenclatures, conventions, but in a sense they all mean either the half plus half spin or the minus half spin. Okay. Now, why do we use them? One major motivation for using them is that it can be very energy efficient. Not only it can avoid the charge dissipations that are associated with the conventional charge transport, but it can also have more efficient manipulation of electronic states, and in this case, the spin states. So therefore, it in a broader perspective, it appears to be a very energy efficient method, and therefore this is very highly studied today. Now, here I have this comparison between magnetic. Again, please read the magnetic devices as spintronic devices. So magnetic or spintronic devices versus semiconducting devices. And again, there are some predominant features here that magnetic devices, for example, rely a lot on interfaces, atomically smooth interfaces. But while semiconductor devices, they rely on the depletion layers, which you are already familiar with. Then there's the spin diffusion lens in case of spintronic or magnetic devices. They also have lower resistivities, and they also have magnetic anisotropies in general. So these are some features. These are not exhaustive, but these are some features that differentiates this kind of devices from semiconducting devices. And both of these are already there in the market. In the pictures here, you will see that the magnetic devices is depicted by the hard disk drives that is there in our computers, or used to be there in most of our computers. Now they have been replaced by solid state ones. And on the right hand side, you see semiconducting devices are represented by these processors. So that was usually the case, that our bulk storage, our most of our information was stored in the magnetic devices in hard disk drives, but now, and the processing was done by the non-magnetic or the semiconducting devices. But today it is a different scenario. Today we have spintronic or magnetic devices storing both the primary memory, secondary memory, as well as doing the processing part. So we will also have a look at that in the coming slides. So just some basic things about the spin, because I said there are two parts of this talk, the spin and the memory. So let us have just a few things, learn a few things about the spin here. So you know that in a conventional electronic device, the a major parameter that or major phenomenon that we are concerned about is the scattering phenomenon, right? And scattering, it gives to rise to the resistance and many other effects in a charge based device. Similar to that, we have a scattering phenomenon in a spintronic device as well. But in this case, the scattering is not symmetrical for both the spins. So the up and the down spin will experience different kinds of scattering events. Some may be preferentially scattered, some may be less preferentially scattered, some may be preferentially scattered in a particular direction, some may be preferentially scattered in a different direction. So those things, sorry, just a moment. Yeah, so as you can see here, the two spins here, the yellow and the green one, they are scattered in two different directions in this spin scattered state, and therefore you have a so-called spin current, right? And this is just one effect to demonstrate that you can have preferential scattering or unsymmetrical scattering in case of spin-based systems. Then another thing that I would like to mention here is the spin orbit interactions. So where the spin and the momentum of the electrons, they get coupled together, and you can have very exciting, exotic, effects or phenomena that can be physically observed because of this interaction or this coupling between the spin and the momentum of the electron, right? We will not go into the details of it because that is not the purpose of this talk. It is a limited talk, so I would like to introduce you to the things, but then people can, we expect that you can always learn more from the resources available, and if there are any questions, we can always take it after that. The next thing is the spin Hall effect. So the interaction, the spin orbit interaction, the scattering that I mentioned before, this can all, I said, manifest into different physical phenomenon. And some of these are called the spin Hall effects. There are many kinds of spin Hall effects. Again, we'll not go into the details of this, but the spin Hall effect or anomalous Hall effect, these are different kinds of effects that comes into picture when we are focused on a magnetic materials that have spin. They can have a symmetric distribution of spin, asymmetric distribution of spin, but in these kind of materials will have this kind of new phenomenon that comes up. So this is different from the Hall effect that many of us are familiar with, where you apply a magnetic field and in the presence of it, when you apply a current, there is charge separation across the surface of the conductor. So this is special effects. This comes into picture only when we are considering spin-based devices or magnetic devices or magnetic materials and so on, right? Next is that there are two very common terms that will come across when you read about spintronic devices or spintronics as a whole. And these two terms are spin transfer torque and spin orbit torque, right? And very simply put, spin transfer torque can be imagined in terms of more of like a conservation of momentum principle, where a spin which is, for example, upspin. If you can see in this picture, if you can see my pointer, that when an electron is flowing, you will see that the spin of the electron gets oriented in this blue, the big thick blue arrow. If there is a spin transfer torque there, it will orient the momentum of this electron, not momentum, sorry, the spin of this electron in the direction of the applied torque, and this torque generates or it comes from the intrinsic spin of the or the magnetization state of the material itself or the device itself, right? So you can imagine that this kind of a torque is applied, and this torque is transferred, or the spin torque is transferred to the incoming electrons, and therefore the orientation of the electron that is moving out is oriented in the direction of the torque applied. This is the spin transfer torque. There is another thing, as I mentioned, the spin orbit torque. Here, a different kind of phenomenon comes, but again, this also tries to orient the spin of an electron in a particular direction. But if you see here in the in the bottom right corner, you can see that when a charge current is passed through one of the bottom layer, it kind of exerts a torque on the spin at the interface. So the yellow material is a magnetic or a ferromagnetic or a ferrimagnetic material, for example, and then the bottom layer is, let's say, heavy metal or some other kind of metal which can generate that kind of a torque by spin orbit interaction. So what it will do is it will try to align the magnetization of the ferromagnet or the electrons in the ferromagnet or the in a particular direction. So it will create some kind of a spin current. Okay, so again, this is another way basically to manipulate the spin in a device, right? So by spin orbit torque. So these two things will you will encounter very often: spin transfer torque and spin orbit torque. And there are already some devices which are using the principle of spin transfer torque. For example, in MRAM devices, we if time permits, we'll have a look at them towards the end of the talk. And also there are other some devices now which are using the spin orbit torque, and reason is the spin orbit torque is more energy efficient. Again, we'll have more comparison between the two in device form and towards the end of the talk. Now I mentioned here spin orbit torque. So the spin orbit torque basically is it has to be engineered, it has to be manipulated, it has to be optimized to get the best efficiencies, best output, and all of this is parameterized in a very critical parameter called the spin Hall angle. The spin Hall angle, which is here denoted by theta sh. So this spin Hall angle is intrinsic to materials, interfaces, alloys. So by depending depending on the kind of material you're using, you can have different spin Hall angles. So for example, here I have noted down some of the spin Hall angles of platinum, tantalum, and tungsten. Now these are different and the signs are also different. We'll come to the sign. But before that, what is this spin Hall angle? So the spin Hall angle is basically can be thought of as the efficiency of conversion of charge current to spin current. So if you see here in this SOT picture that I've shown, the charge current is passed from the left to the right? And there is a spin current is generated because the red and the blue, that is up and the down spin, or the two different kinds of spin, are separated. So since they're separated, there is a net spin current, right? So this net spin current that we are having is generated from the charge current. So the efficiency of conversion from the charge current to the spin current is called the spin Hall angle, or is measured by the spin Hall angle, right? And different materials have different spin Hall angles. And as I said, the sign is basically it's again another convention, and it indicates the direction in which you are generating the spin current. But we can ignore the spin for now. Let us only focus on the sign for now and only focus on the strength. So if you look at the strength, tungsten has the highest strength. Tantalum, platinum seems to have similar strengths. But then again, these are some nominal values picked up from literature. There is always a variation in this depending on the material quality. The key word here is the material. So for all these devices, the very basic a lot of work goes into the development of these materials. So just to emphasize on that part, I will spend a little part, a small portion of this talk on delving into this importance of this material for spin orbit torques. And so is the case for any other field in spintronics. A lot of effort goes on the material development, right? So, for example, this is a periodic table that there are so many elements that exist in the periodic table, and there is a graph on the right hand side, and you can see that the spin orbit coupling strength versus the atomic number is mentioned there, and so basically what we can understand from this graph or in general is that there are certain materials which have very high spin orbit interaction strength, right? The lambda in this case. And these are the materials that are of interest to us because they kind of can, transfer this momentum of the electron into the spin and therefore, couple them, and then we can have this the spin Hall effects and so on, the spin orbit torque. So, therefore, these are the materials that are very important to us, or let's say critical to us for our purpose. So, we try to find them and we try to experiment with them. Now, these are different materials, again, another list. But here, what we have done is we have mixed certain materials with certain other materials. We have basically created alloys, right? So, the spin Hall efficiency, which is, or the spin Hall angle, which is basically the ratio of the spin current by the charge current. Now, this you can see is that the SOT efficiency or the spin Hall angle, they vary, and I mean in the next slide I will show that how they vary on alloying. But you can see that a lot of alloys have been experimented with, where two different, sometimes three different materials have been mixed together to harness higher spin orbit torque, right? Now, there is another thing that is done to improve the spin orbit torque or the spin orbit capabilities of these materials. That is called oxidation. It has been observed that oxidizing these materials on the interface, on the surface, leads to better, preferential scattering of certain spins, and therefore helps us in increasing the spin current that we are generating. Also, if we have seen that sometimes very thin interfaces. So, for example, on the oxide part, the examples are of tungsten oxide, platinum oxide, and cobalt platinum oxide. And in the next slide, I will show you how it has increased. But you can see that platinum in the beginning was 0.1. The pure platinum, the bulk platinum SOT was, or the spin Hall angle was 0.1. But here, platinum on oxidation is giving 9 times higher, so it's 0.9. So quite a increase, right? Similar will be the case for all the other metals as well, or metal alloys, or mostly, let's say, that is what we observe. Similarly, for multi-layer, you will see that again, platinum, when we have made an interface with hafnium, we see that we can have higher spin Hall angles, right? So these are so the left hand side, the oxidation is a result of oxidation, and on the right hand side, it is a result of interfacial scattering. Now, here from the last three slides, we have taken these values and we are comparing them. So if you see for platinum, it was 0.10 for the pure platinum. When we alloyed it with copper, we here the increase, when it decreased rather, so it did not increase. With gold, we see it to increase. With aluminium, there is a 40% increase, marginal increase. Hafnium, again, we have some increase. Similarly, when we oxidize it, we oxidize platinum, we get even higher spin Hall angles, right? And with multi-layer of platinum with hafnium, again, we get very high spin Hall angles. Same is the case when you look at tantalum and tungsten. So basically, by alloying, by oxidation, by using multi-layer interfaces, we can have, or we can increase the spin Hall angle. So a lot of the work in this field is focused on increasing the spin Hall angle and therefore the spin orbit torque in these devices. Now, I would like to emphasize here that by increasing the spin Hall angle, by increasing the spin Hall efficiency, what we are doing is we are making the device
Tanmay sir, you are muted. We are not able to hear you.
Yeah, someone else muted me. I did not mute myself. Hello.
Now it's audible.
Can you hear me? Okay, fine. So, yeah, I was saying that by doing all this kind of engineering on these materials, we can harness the higher spin Hall angles, spin Hall efficiencies, and therefore we can make more energy efficient devices, right? But again, this is only the surface of it. There's a lot of details that lies beneath it. But I think it at least gives you an idea how the material development follows in this kind of material devices. Okay, so the until last slide I mentioned about alloying with heavy metals, interfacing with heavy metals, and oxidation. Now there are other ways as well to harness higher spin Hall angles or higher spin Hall efficiencies, and that is one of them. For example, is using new kinds of materials which are recently. I mean, they were known before, but then recently a lot new information has surfaced about this kind of materials, which you are familiar with 2D materials, I'm pretty sure. So then there are these topological insulators, something called wild semi-metals. So these are all different kinds of materials which have very exotic properties, and they were known before, but then many new properties regarding them are coming to light now, and then they are being subsequently used, for example, to generate or harness the power of spin here. So we can have higher charge to spin conversion efficiencies with them. The next thing is, yeah, so here I'm just showing that some kind of comparison between topological insulator versus heavy metals. So platinum, palladium, or tantalum, those kind of heavy metals versus the topological insulator. So here there is an example of bismuth selenide, bismuth antimony, and bismuth tellurite, or some alloys, right? So you will see that the spin Hall angles of as large as 425 has been reported, right? I mean, it is like way higher than what we have been able to see in heavy metals. So to summarize this slide, by introducing new kinds of materials which have very interesting properties, we can actually have more efficiency in our charge to spin conversions, right? Okay, this is one slide that shows the comparison between different kinds I mean, material prepared by different or different kinds of materials, let's say. So the black squares are the topological insulators, the red ones are heavy metals. Then you have the blue triangles, they're the 2D materials, and then there are some Rashba interfaces. Let's ignore that, we have not talked about it. And there are antiferromagnets. And I think in the next talk, Dr. Binoy will talk about some antiferromagnets. You might have some idea from there as well. But the point I'm trying to make here is that by using different kinds of materials, we can have different kinds of SOT efficiencies. So for example, topological insulators, you will see that they have very high efficiencies in the SOT efficiencies. They are quite on the larger side, right? But they have one downside on that part, that they have higher resistivity. So we need to therefore also keep into account that just having very high spin Hall efficiencies is not the end of it. There are other parameters which needs to be taken into account. So when you have high spin Hall angle, but then you have very high resistivity of these devices, in the end you also end up having very high you might also end up having very high power consumption, as you can see in the next graph on the graph B. So we need to therefore focus on this part where the power consumption versus SOT efficiency is plotted, and we want to focus on this right hand bottom corner where we want to have the lowest power consumption, but at the same time very high SOT efficiencies. And you can see there are a lot of black squares here. So basically topological materials have so far been have indicated a lot of promise for this. And yeah, so bismuth selenide is in one of my works. We have used bismuth selenide, and we have been able to demonstrate this kind of low power consumption, high SOT efficiencies. And I'm not showing the work here, but if you're interested, you can always find it. I can also drop the link on the Teams chat. And in last few years, what we have been also able to achieve is that unlike before, when these materials like topological insulators and 2D materials, they needed to be deposit. I mean, there were not, let's say, semiconductor compatible processes to really do those or develop those thin films. But today we are able to successfully do it through sputtering and really develop very high quality films. Many groups worldwide have already done it. We were one of the first ones to do it when we had done it in Singapore. So yeah, so this is really a very interesting part of this domain now going ahead. Okay, so I just mentioned 2D materials, while semi-metals are other different. Again, this kind of materials have also shown a lot of promise for generation of spin orbit torque and therefore high spin Hall efficiencies. And yeah, so I have, I think, also mentioned already this thing, so I will just skip this one for now. Yeah, this slide, yeah, so a lot of concern now therefore is how to integrate them with the conventional CMOS technology, because at the end of the day, it has to translate into products, and when translating into products, the high spin Hall angle or just the low power consumption is not enough, and we need to really figure out how this can be integrated with the current technology, with the existing production lines, with minimum change in them. At the same time, also there are these back BOL processes, and there are temperatures associated with it. How stable these our materials are, our films are to those temperature, system processes. This is all that we need to now take into account when we are going into the integration with CMOS or the industrial integration of it. But again, those are very complicated things. Will take days to really discuss about them at length. But we should keep in mind that just from research perspective, just getting very high spin Hall angles or SOT efficiency is not the end of the world. We need to really also think about integration with the CMOS technology. Now, I mentioned that there are many kind of spintronic devices, and we have harnessed spin to create spin valves, memory devices, sensors, many kind of things are there. And here I just wanted to bring to your notice that even we can we can use them for energy harvesting, where you can use heat to generate spin currents. We can use them as sensors for temperature. So there is also another part of it where there is something called spin caloritronics, where heat based spin manipulation, or spin plus heat or heat transfer is also another domain there. So it's a very broad domain of spintronics, and I wanted to show this one because this kind of stands out from the other domains, but there are so many other domains in spin based devices. This we do not have enough time to really glimpse at all of them, but if it garners your interest, please go ahead and have a look. There are many good review papers out there, and you can learn a lot from them. So yeah, so the next part of the talk is on memory, and we all know what memory is. At least vaguely we know what when we say memory, what we mean. It's basically the ability to retain data, right? Be it in our minds, be it in devices. It is basically basically data retention. Now we in terms of memory storage, memory devices, we very often refer to something called the memory hierarchy, and this is this pyramid, this is this triangle, if you call, as you can see here. And here there are three different aspects that are taken into account. One is the storage capacity. How big is the storage capacity? How big it can store? The cost of it, what is the per unit bit cost that we need to pay for storing information. And the third thing is the access time. So if you look at this triangle or this pyramid, the technologies or the devices that are sitting at the top, so the registers, the cache, the main memory, they are of the highest speeds. Okay, so they have highest data transfer speeds, data fetching, it's the highest there. And at the bottom part, you will see the ones that are slower. They're comparatively slower. They take On the top of the pyramid, you operate at nanoseconds. On the bottom of the pyramid, you probably work in milli to microseconds. So there is a huge distribution here, and probably this pyramid is not also exhaustive. It doesn't include all the devices that are there, but it kind of gives you an idea about how to classify different kinds of devices. Now, if you can see at the bottom of the device, this traditional disk, it basically refers to the hard disk drives that you have in your computers, or maybe not in laptops anymore, but at least in computers you still have this traditional hard disk, your servers, traditional hard disks. But at the bottom of the pyramid, so top of the pyramid are the main memory. So here probably here it is, for example, the RAM, which again all of us are familiar with, the random access memory. They have higher speeds, but the storage capacity is less. So the top you go, the storage capacity is less, but they are faster, but they're also expensive. And the bottom you come, they have more storage capacity, they are slower in access, but they have they are very cheap comparatively. Okay, so now what sits where? So here on the right hand side, some examples are given. So you see the secondary storage is the hard disk drive here, and then on the middle you have the flash, then on the top you have the RAMs, and then the processors and so on. So this is how the products are for different kinds of for the different slabs here in the pyramid. Okay, so here again, a lot of emphasis today is on energy efficiency, right? Everything that we talk about is of energy efficiency, and today in this digital world, a lot of energy of that humanity is using is actually being spent on storing, retrieving, and processing information. Probably I missed the generation part. So generation, storing, retrieving, and processing information. So these are the four things in which we are probably using almost half of the energy that mankind is using today. And therefore, it becomes very important that we use this energy judiciously, make as energy efficient devices as possible. So if you look at therefore this graph, on the left hand side we have the density. That means the storage density. The higher the density, that means the more is the storage capacity in a limited area. And on the x-axis you have the energy consumption. So we would like to operate in a region where we have the highest density, but at the same time we have the lowest energy consumption, right? So that is where we would like to operate, and that would be at the top right corner. So that is where our work on our focus should be, but no, that's very expensive. As I had mentioned in my last in the last slide, that it is very expensive to operate in that region. But at least somewhere in this triangle, if we operate somewhere for secondary memory, if we can operate somewhere, let's say here, but on primary memory we operate there. So that kind of thing would probably be a more realistic scenario for us. So we don't want to be on this side of the of this graph. We want to be on the yellow, the shaded region. That is where we want to operate in all our memory and processing. Okay, so hard disk drives, you're all familiar. I think I will quickly go through these slides. So I just wanted you to give a glimpse. So this is how it looks inside the disk. There's been a lot of development that has taken place over the years. It started all the way with the first computer called RAMAC in 1956. And then since then we have been increasing. We have a market where SSD versus HDD is now SSD versus HDD is a very big debate. Still HDDs are cheaper, SSDs are still expensive, but way cheaper than what used to be before. And yeah, so we started with disks of this big size to just store a few kilobytes of data. If you see how big it is like 24-inch, so it is kind of like my face can actually fit in the center disk of this center of this disk. So it's so big, right? Yeah, so then we had this kind of magnetic recording technologies. They have advanced over the years, and yeah, so they have advanced over the years. I would just like to show, spend a few seconds on or minutes on this slide. So a major problem with this advancement of technology in hard disk drives or in storage was of something called this magnetic trilemma, where you want to have higher signal to noise ratio. We want to have higher thermal stability because data retention or data stability depends on thermal stability. And then we want to have easy writability, where we want to write and write the information and rewrite the information easily with less energy. So these are all conflicting requirements, and therefore it is a trilemma. As you can see, they're all interrelated, and they some most of the times oppose each other. So it's all very delicate balance that is maintained there. And two important technologies I will mention here, which are already in the market today, are heat assisted magnetic recording and bit pattern media. So many of our hard disks, especially from Western Digital and Seagate today, are coming in the form of heat assisted magnetic recording. So therefore, I wanted to spend a few minutes on this because we should be familiar with the state of the art technology today. So here, what is done is that some kind of laser heating is used. Very small laser spots are used to temporarily heat the magnetic bits in a hard disk device, right? And it is temporarily moved from its stable state to something called a near paramagnetic state. Let us not go into what that paramagnetic state is, but to something called a near paramagnetic state, and then an magnetic field is applied. As you can see with the yellow pole here, a magnetic field is applied, and that helps in switching the desired bits at very low fields. So basically, the writability issue is solved, and because laser is used, right, to reduce the thermal stability. So inherently a very highly stable material can be used, high thermal stability material can be used, but the assistance in switching or assistance in writing information is provided by the laser. So the magnetic field is assisted by the laser in writing. So this is therefore called the heat assisted magnetic recording, right? And there are again many ways of delivering that heat. There are near field transducers that are used. There are some pixels, some cavities that are used, right? So optical cavities. So there are many ways of delivering that power to the bits. But at the end delivery point, it is basically manifested as heat, and the region is heated up, right? And then that's when your magnetic state is changed from, as you can see, the magnetic stability, let's say, is coming down. And as you are increasing the temperature to the right hand side, the magnetic stability comes down, right? And you reach a region where the available right field can write it very reliably. And then you let it cool down so it goes back to its stable state again. So this is the way, this is the current recording technology takes place in most of the hard disk drives, right? And yeah, this is a TM image of the site that shows how many layers are there. These are very critical layers. They are developed or deposited with very state-of-the-art technology, right? And our so that's when the entire process is carried out in clean rooms with very sophisticated equipments. And yeah, so then the other thing is the bit pattern media, where you use very individual physical regions to represent one information of bit. So you can see that the top and the bottom pictures, if I compare them, so in a hammer media or any conventional media, you would have a lot of physical grains, let's say. A lot of physical grains will come together to form one bit or one domain. But in case of a bit pattern media, each domain or each bit is physically separated. So that I hope you can understand the distinction here, that how a bit pattern media is different from a conventional media or a hammer media also. Right, so that's when you again have very high stability, and if there is easy writability in bit pattern media as well. So these are the two kinds of very state-of-the-art technologies that are already either in the market or in very advanced stages of being produced. Okay, so I'll skip these challenges in bit pattern media, but if you see through my slides, you can understand that a lot of it is dependent on patterning. And a lot of things, a lot of state-of-the-art technologies are developed in lithography and in patterning to solve those issues. Now, yeah, so here I have a slide. So going now, we have discussed in the last few slides, we had a look at the magnetic devices which are used for secondary storage, so hard disk drives, right? Now we will go into the magnetic devices which are used for storing, which are used as primary memory. So, for example, RAM. So, magnetic RAM or MRAM. Okay, so that is serves as the primary memory in our devices today. So, or in our laptops, computers, right? So, before we venture into that again, so let me remind you that again, this magnetic RAM is driven by spin, right? It's spin dependent. It is a kind of a spintronic device, and therefore we need to have the concept of the spin currents. Okay, so on the you have A, B, C, and D, and you can see that the first one is an unpolarized current. Basically, there is no spin there. So you have equal number of upspin and equal number of downspin. So the net spin current is zero, but you have 4 charge. So if I consider the charge here, it's 4q, let's say, right? So that's a 4 q by t times by t charge current, right? Then if you go over to the polarized current, you see that there is a asymmetry here. There are more upspins than downspins. So there is a net spin current. Fully spin polarized current, there is no downspin at all, right? It's completely upspin. So completely there is spin current, there is charge current. Okay. But in pure spin current, you have equal number of up and down spins, but they are moving in the opposite direction. So the current caused by them is in the opposite direction. So therefore, the net charge current is zero, but the net spin current is 4 units here. So if you therefore the best ideal thing to do in or let's say most energy efficient thing to do would be to have pure spin currents, and that would be suitable for some many applications but may not be suitable for many applications as well. But you can understand that why pure spin current can have zero dissipation of heat, and we can have, or not zero, but at least a very low dissipation of heat, and we can have we can manipulate the devices by using pure spin current. So our work would be done with very low energy dissipations. Now, as I said, for MRAM, there are many contenders, many kinds of technologies have been are being studied, have already been studied for the non-volatile memory technologies in terms of MRAM, for example, magnetic RAMs. And one is the phase change memory, right, where different the material changes its phase depending on the kind of environment around it in terms of charge or in terms of magnetic field. Then we have the RRAM, and then we have the MRAM, right, STT-MRAM, and then we have the FERAM, right? So these are different kinds of emerging non-volatile memory technologies. For example, STT-MRAM is already a product, so it is already used, you know, in the, I mean, it is used in our computers, already mass manufactured by companies. So this is a completely commercialized product already. Some of these are also made in small quantities, or I mean very large scale devices, not very optimized, but some of the other ones may also be very soon be optimized. We will not go into the details of how they operate and all, because that would again take a lot of time. But we would only focus, let's say, on the STT MRAM part here, or let's say only the MRAM part here, because the MRAM can also be STT and SOT, as I had mentioned to you before. And I wanted to just have spent some time on this slide here, where I wanted to show you that, for example, this is a junction where you have two magnetic layers, right? So these white arrows, when they are what they're pointing to, the white arrows are pointing to the magnetic direction or magnetic orientation of this two layers, for example. Okay, and the layer in between is a non-magnetic layer, or called a barrier. Now this barrier can be oxide or tunneling barrier. It can also be a non-oxidic conductive scattering barrier. Both are possible. However, let us just consider it as a barrier at this point. And what we are trying to show here is that when an electron flows, right, from one end to the other, some of them will preferentially be allowed to flow. Okay, some of the electrons, depending on the spin, in this case, let's say the up spin is preferentially allowed to flow, while the down spin is actually rejected, or let's say reflected in a way from the beginning itself, right? So therefore this but on the other side, you see that when the electron is flowing from the other hand, on the right hand side, we see that both the, when it is faced with both the electrons, both of them are allowed in, but then the scattering takes place at the junction. But basically here that let us simply understand that it kind of acts as a kind of a filter, and also depends on which side the electron is coming from, and then this will help you to switch from one state. So here you see that both of them are now switched into a parallel state, right? So they are all both of them are in the same orientation, because basically the there was kind of a torque transfer here, and the magnetization of the layer here, or the free layer in this case, right? FL is a free layer, is changed from one orientation to the other. So this kind of manipulations can be done. So if you apply enough spin current, you can also manipulate it. If not, if you're not applying enough spin current to manipulate it or transfer the momentum, you can also have something called the magnetoresistance, right? So the so if you can see in this slide, right? So if you see here, the resistance that these electrons, or the up and down electrons, are facing is different depending on the kind of layer orientations that we have. So when they are both parallel, we have so the up spin, for example, can easily flow through, but the down spin faces resistance, right? But when we have anti-parallel, both the up spin and the down spin, yes.
So we are running out of time probably.
Fine. Can you give me 1 to 2 minutes? Is that okay? Or
Yeah, sure, sir. Sure.
okay, thank you. So here you can see that on bottom part, that in figure B, that the up and the down, both the spins are facing resistance at some point. So in this anti-parallel state, overall there is a high resistance. In the parallel state, at least one of the orientations have very smooth transition or smooth movement, and they have low resistance. So this is a schematic which kind of at least gives you an idea that the parallel orientation here will have low resistance. The anti-parallel state will have high resistance, which translates into something called the magnetoresistance. Okay, and therefore this can be used as kind of a binary state of 1 or 0. These days, these kind of devices are also used for non-binary states, where you can also actually host multiple states. But then I mean, just for information, you can always find more about that. So I will go through this, I'll skip through this, but this just wants to emphasize that the barrier can be tunneling, and maybe many of you are already familiar with what tunneling is, so you would already understand. So yeah, and this is the magnetoresistance again is modeled in terms of this two current or two channel model, when you can see here that in the parallel state, at least one channel, the upper channel, if you can see my pointer, has the low resistance, but in the anti-parallel state, both the channels have at least one high resistance. So therefore the net resistance in an anti-parallel will always be higher than the parallel state.